Have you ever wondered why some elements react easily while others don't react at all? Why hydrogen bonds so quickly with oxygen to form water, but helium just floats around doing nothing? Well, the answer lies in one word: valency. Valency tells us how many electrons an atom needs to gain, lose, or share to become stable. Most atoms want their outermost shell, also called the valence shell, to be full. For many atoms, that means having 8 electrons in that outer shell. This is called the octet rule. Now consider this: neon already has 8 electrons in its outermost shell. It's happy. It doesn't want to bond, so its valency is 0. On the other hand, sodium has just 1 electron in its outer shell. It would rather lose that 1 electron and settle with a full inner shell. So its valency is 1. Valency is like an atom's social need, how many connections it wants to make to feel complete. Now, meet the actual players responsible for chemical bonding: valence electrons. These are the electrons sitting in the outermost shell of an atom. Let's imagine the atom as a party, and the valence electrons are the people near the exits, always ready to leave or bring someone in. They're reactive. They decide whether the atom will bond and how. If an atom has 1, 2, or 3 valence electrons, it usually loses them to become stable, forming positive ions. If it has 5, 6, or 7, it gains electrons to complete the octet, forming negative ions. And what about atoms like carbon with 4 valence electrons? They usually share electrons, forming covalent bonds. That's why sodium, with 1 valence electron, and chlorine, with 7, react so well. Sodium donates 1, chlorine accepts 1. And just like that, you have table salt, NaCl. Let's zoom into the rule behind all this: the octet rule. Atoms are always trying to reach a state where their outer shell has 8 electrons, just like noble gases. That's the sweet spot of stability. Take fluorine, for example. It has 7 valence electrons. To reach 8, it just needs 1 more, so its valency is 1. Magnesium has 2 valence electrons. Instead of gaining 6, it's easier for magnesium to lose 2, so its valency is 2. And neon? It already has a full octet, 8 electrons in its outer shell. It doesn't need to gain or lose anything. That's why neon doesn't form compounds. Its valency is 0. So valency isn't just about counting electrons. It's about finding the most energy efficient way to get to a full outer shell. Now, how do we calculate valency? Here's the simple rule: if an atom has 1 to 4 valence electrons, its valency is equal to that number. If it has 5 to 7, the valency equals 8 minus the number of valence electrons. Let's try a few examples. Oxygen has 6 valence electrons. 8 minus 6 gives us 2. So oxygen has a valency of 2. Carbon has 4 valence electrons. Since it's right in the middle, it tends to share them. So its valency is 4. Fluorine has 7 valence electrons. 8 minus 7 equals 1. So its valency is 1. Diagram on screen. You'll see the electron dot structures of oxygen and fluorine here, each showing how many electrons they want to gain to achieve an octet. So how do these ideas play out across the periodic table? Let's take the first 18 elements. Hydrogen, lithium, and sodium all have 1 valence electron, so their valency is 1. Magnesium and calcium each have 2 valence electrons, so their valency is 2. Aluminium has 3, carbon has 4, oxygen has 6, and fluorine has 7. And we use the octet rule to find their valencies. Some elements even show variable valency, like phosphorus, which can have a valency of 3 or 5 depending on the compound it's forming. You can refer to table 4.1 in your book for a full list. It gives electron distribution and valency for all the first 18 elements. Let's wrap it up. Valency is the backbone of chemistry. It tells us how atoms bond, how molecules form, and how compounds behave. Whether it's water, carbon dioxide, ammonia, or hydrochloric acid, every compound is based on the valency of its atoms. Atoms gain, lose, or share electrons to fill their outer shells. And the number of electrons involved, that's the atom's valency. It explains why oxygen forms two bonds in water, why carbon forms four in methane, and why noble gases don't form bonds at all. So the next time you look at a chemical formula, think of valency as the quiet architect behind every molecular structure. I hope this session helped you see how valency is the key to unlocking why atoms behave the way they do, from the salt in your food to the oxygen in your breath. See you in the next class with more insights into the world of chemistry.